In that case, I'll move on to introduce Colonel Gordon Fullerton, who got his bachelor's and master's degree from Caltech in mechanical engineering, did ROTC, and went on to the Air Force, where, well, I guess he has flown in the course of his career about 135 different types of airplanes, 16,000 flying hours. He flew F-86 interceptors, B-47 bombers before going to Air Force Test Pilot School in the mid-60s. In '66, he was chosen by the Air Force for the Manned Orbiting Laboratory, which was going to be the Air Force's space station. That program was canceled in 1969, and the MOL, some of the MOL astronauts came over to NASA and became NASA astronauts. That was in the heyday of Apollo, and Gordon was support crew on the last 4 Apollo missions. Then went on to be the test pilot on 3 of the first 5 approach and landing tests. If you remember, that's when the Shuttle Enterprise, which was not designed for orbital flight but was designed to test basically the last 50,000 feet down to the ground, was dropped from the 747. Went on to pilot the 3rd shuttle flight, which was one of the orbital flight tests. That was the flight which landed in New Mexico, and then commanded STS-51F, which was the first it was the first flight of the instrument pointing system. That was also the flight, I'm trying to think, that was the flight where you lost the engine. Yeah, which we talked about. That was the one flight where we had an engine shutdown, and we went over that in some detail. So they've heard. So that was, well, that's fine. I mean, because I think they should hear about it from what it seemed like inside the cockpit now that they've heard kind of the technical details. In any case, after leaving the astronaut office, Gordon has moved into Pilot's Heaven, which is Edwards Air Force Base and the Dryden Test Flight Center, where he basically spends all his time, well, not all of his time, because there's management stuff as well. Unfortunately, that's the price you pay. But basically, he gets to fly airplanes for a living, and lots of different kinds, including the carrier aircraft and the B-52, which launches various test aircraft and a whole bunch of other airplanes. So if you remember, in the whole systems engineering approach to things, we talk about the conceive, design, manufacture, test, and operation. So this is basically the final lecture, and this is the test and operation of the space shuttle from a pilot's point of view. So with that, I'll give it to you, Gordon.
Okay, thanks. I was sitting in your place back in 1958 when I was a grad student at Caltech for a year before heading off to the Air Force. Well, almost 50 years ago. But the real blessing of my life is to be able to do what I love to do for as long as I've done it, beyond all reason. And anyway, I hope to share some of that with you this morning. This is my first time through this pitch. Feel free to holler out any questions as we go, and we'll stumble through it together. I plan to talk about 3 different phases of the orbiter test program. The first were called ALT, the approach and landing tests. They consisted of really 13 flights, 5 captive inert flights where the Enterprise was flown on top of the 747, but nobody in the cockpit. The controls were locked. That was to clear the envelope for the kind kind of unlikely looking combination of a 7.4 with a orbiter on top. Then there were three captive active flights where we were manned up in the orbiter where the system's running, the electronics, the hydraulics were active. The controls were free to move a little bit, not full throw. And we also determined how high the combination could get, because altitude was, and it wasn't 50,000 feet, it was more like 28,000 feet max, even with the 7.4 engines overboosted. That followed by 5 free flights where we actually pushed the button, launched off the top, and glided to a landing. The orbital flight test part of the shuttle program, OFT, consisted of 4 flights, STSs 1 through 4, of varying durations. The first STS-1 was planned for just a couple days, get up and get down and have a look at how things looked after it flew. STS-2 was supposed to be 5 days. They had a fuel cell problem that cut their flight short, unfortunately for the crew. Then I was on STS-3. We were scheduled for 7 days, and because of a raging dust storm at the planned landing site, we got an extra day, a real blessing. With no tests to do, we had a free day in orbit, and ended up with 8 days. STS-4 planned and flew 7 days, landing on the 4th of July with President Reagan out there to watch. And then we get into operational flights, of which there have been a lot, something from over 100. The last flight to fly, the return to flight, was STS-114, but the numbering system went through a couple phases, so there haven't been 114 flights. I don't know how many it has been, but there have been a bunch. So I'll talk about 3 of the, well, more than 3 flights, but the ALT flights. The crew patch, you always got to have a crew patch. That's a major hurdle that you have to overcome when you're assigned to a crew, is get the patch designed and then get it approved by upper management. My part of the OFT, STS-3 in 1982, and finally then an operational flight, 51F in 1985. My job prior to any of these flights I worked into was a dream job for really system engineering, I guess, and for a pilot. I'd been to test pilot school. I was intrigued with all the airplanes I flew with a cockpit design, and was very aware of the flaws of cockpit design. Seems like sometimes engineers lay awake nights trying to make it hard to operate subsystems. So I got in at the beginning of the orbiter crew interface and became, before it was over, sort of the czar, was responsible to sign off all the drawings, lots of reviews. It was a great responsibility because I was immediately and early into subsystem design, because you have to know what the subsystem does to make any intelligent choice of what the controls and displays should be. This is a view of an orbit, not the Enterprise, but probably the, I don't know whether it's a simulator or the real airplane. They look alike, but one of the orbital capable shuttles. This is like the little old ladies always say when you're out on static display for Armed Forces Day, and oh, look at all the things, how do you remember what they all do? Well, that really is a challenge to make things straightforward, and I became painfully aware, especially later on, when we had a lot of experiments coming in, that engineers in their little ivory tower building a system in the lab are so totally personally familiar with how their stuff works that it doesn't bother them that the switches are unlabeled or labeled illogically, and they bring that all in and want to put it in the orbiter, and when the crew says, wait a minute, I have to remember that before I turn on switch A, switch C and D have got to be turned on in this order or the whole thing will blow up. And they say, oh yeah, that's the way it is. And they know it so well personally. And yet, when you're overwhelmed with a whole lot of experiments, I'm sure you ran into it on your flight, that all the stuff that is just totally familiar to the guy that invented it becomes a challenge when you're faced with a whole lot of them, a limited amount of time to learn it. And so standardization of what the scheme, especially in the software, well, there are a lot of gadgets. In fact, if you count all the switches, gauges, circuit breakers, upstairs, downstairs, and the mid-deck, there's about 2,100 total in the orbiter cockpit. But the real challenge is what shows up on the screens here. And so the software was a bigger thing in making them all play together. Here's a higher view, and the overhead panel above your head in a forward cockpit has a lot of other switches. An example of what I'm talking about, this array of switches right here controls the reaction control system valving, and then the orbital maneuvering system. Back in Apollo, which I worked on when I first came to Johnson Space Center, I learned while lying many hours in the Apollo crew simulator that had the worst cockpit ever designed by man. As an example, it had a pressurization system, a helium pressurization system to push the propellants for the reaction control jets out of the tanks, and then the valves that went to the various array of thrusters all around the command module. And one would think logically, okay, if you have something to turn on the helium, you label that helium on, off. And then the manifold, the next branch in the Christmas tree manifold would be System A versus System B or something like that. And in fact, it had names like that, but they put the switches in a long row and they labeled them A through H right there on the panel. No clue as to what you were throwing, so every move you made in the cockpit, and some of these things were critical, required you to either be, a mental giant or open a checklist and say, okay, to pressurize System B, I've got to throw B on, and then A next, and then H last, or something like that. So, obviously unacceptable, and became my career and mania to try to improve that. The first orbiter simulator built was called the OAS, Orbiter Aeroflight Simulator. It was on a moving base platform like the standard airline simulators you see today. This is Fred Hayes and I sitting in the cockpit. This one was built originally to be the Enterprise, and the Enterprise was OV-101 in the scheme of things, a numbering of orbiters as they were built. 101 had only the systems it needed to fly approach and landing tests. The plan was to retrofit it later to make it into an orbit capable, but for the ALT program, it had just what you needed and only that to fly in the atmosphere. Very short flights. But this is our first chance to look at what we had and what we're getting into as far as pilot concerns. Now, I guess you've had all the subsystems, right? You're all completely briefed and experts on subsystems by the people that have preceded me here in the course. I'll give you, though, a quick review here. The avionics system, the shuttle is built with inside the outer mold line as the pressure vessel that is roughly back to the forward bulkhead of the payload bay, and is embedded inside the basically aluminum structure with a thermal protection system applied to the outside. And most of the avionics are in racks right up here, right in there with you in the cockpit on the mid deck. The stowage lockers are aft of the racks full of black boxes and lots of wires. And the other place there were avionics is back here, just aft of the aft bulkhead of the payload bay, and there's some areas where they put items like rate gyros and accelerometers a long way back. From a systems engineering standpoint, Fred Hayes and I were out at Palmdale where they built all the orbiters. Late one night, seems like the testing always happens after 2 a.m. The tests would run round the clock, and we were out there way after midnight in the cockpit participating in the first time they're going to close the loop between the rate gyros and the flight control system, which is contained back up here in the nose, in the general purpose computers. The whole orbiter was suspended on some big air-filled bags, so it had compliance to move. And the hydraulic system was on, powered by a facility hydraulic source. So the elevons were powered, and the rudder speed brake was powered, and the process let us down for the very first time that we're going to close the loop between the software up here and the rate gyros, particularly accelerometers mounted back in the back. And it was a milestone, and we had people stationed around the back to see if anything spit out hydraulic fluid or whatever. Anyway, we went up to the glare shield, pushed the button to go into CSS, control stick steering, which hooked the stick up now to the flight control system. I'll never forget. We pushed the button, and a rumble started. And the rumble built very rapidly to a violent rumble. I mean, we were being bounced around the cockpit. This is 150,000 pounds of airplane is dancing on these rubber bags. And it didn't take us long to say, this doesn't feel good. We pulled the button of down modes back to direct control so there's no feedback. And the upshot of it was that these rate gyros are mounted on this flexible bulkhead, and that hadn't been taken into account properly. And so there was a structural resonance that was just diversion. In spite of all the ground tests down at Downey and the Ironbird mock-ups and everything, when we put it in the real airplane, it tried to jump off the supports. And Fred and I were in the cockpit, and our eyes were big, and we called the control room, which were people back in an adjacent room. Seems like most spacecraft tests traditionally are done. The engineers are all locked in a windowless room, no view of the real hardware down at the Cape. They're miles away. When the spacecraft's either out on the pad or in the main checkout building. And so they said, no, procedure says this is okay. We want you to re-engage. So we tried one more time, and this time the guys stationed in back that were watching said, this doesn't look good. They started hollering on the loop, so we pitched it off. And we went into a raging argument whether we need to complete this test, the engineers were saying, and we're saying, we don't want to break something. And they got people out of bed down in Downey, California, controls engineers, and so it was a memorable night. The resolution was finally a redesign of the mounting area back there, and a reanalysis of the vibrational modes of the F bulkhead to sort it all out. Here's what we had back in for crew interface. You saw in the earlier picture, up front 3 CRTs, monochrome, green. That was either green or nothing on the screen. And we had a keyboard, 2 keyboards, 3 CRTs. So there's always this little concern when you're punching on a keyboard. You want to be sure it's selected to the CRT you think you're doing something on. Another marginal design, but that's what we ended up with. You notice we got a hexadecimal keyboard here. We got some strange keys called item and electric and ops, which had to do with this truly unique way you cause things to happen through software, and lots of things were critical through software. And then this rather dim green screen. This was way before the days, I guess Bill Gates was still here at MIT, or maybe even hadn't registered yet. I don't know. It was way before Windows 1.0. And so it seems almost comical now when you compare it to even modern airliner crew interface with glass cockpits, but we were breaking new ground here. And it even at the time seemed antiquated, because that's all they were willing to embrace in the way of computer control and design. And it was unique, and it caused lots of headaches and delays. The big thing about the orbiter with its I'll go back. Data processing system, the decision was made that everything is going to be done in these all-powerful general-purpose computers, of which there were 5 in an array that worked together. Flight control, system management, navigation, inertial subsystem control of everything. And so the result was the software loads as they were built had lots of flaws when they came down, yet we couldn't fix them. You know, we had cases as dumb as a display that showed the Freon loop A pump on, and when it got through all the software build, it was backwards. It would say off when it was really on. Seemed like a simple fix, right? Go back to the programmer and rewrite the code. But we couldn't do it. We had to live with it for a long period of time through training until another whole load was built, because the load that would fix this dumb little bi-level mistake was also the one that steered you during ascent. And I didn't want to, so everything was frozen, and there was great fear of changing anything that would ricochet through something truly critical. And so even when we got to STS-3, we flew with a book about this thick of program notes that told you, line after line, what was wrong, you know, what was backwards, what was a trap, and really a big challenge for the crew to embrace and live with, because there just wasn't time in the program to build another load, check it out through all the different labs that had to certify it. That's a vote for modular software, where you can change something here and be assured you're not bollocksing up something else in the same machine. OHM's RCS. This is the 2 pods on either side of the vertical tail. Are a couple big OHM's propellant tanks, oxidizer and fuel, hypergolic. So we didn't need any ignition system. As soon as these came together in a thruster, you had thrust. And there were, I think, 44 main thrusters. Here's 4 yaw jets firing out to the side. This would be pitch jets, the same thing repeated on the other side. And up in the nose of the forward RCS, so they had jets that fired up and out to the side and down. And I mentioned the controls in the cockpit, which we did. One of my great successes was getting the orbiter panels to be arranged in a plumbing layout so that you could see what you're pressurizing when you turned on the helium for a given leg and that sort of thing. Helium tanks are what pressurized, and a really clever system of ullage control. That is, when you're in 0G and you got propellant floating around randomly, and you turn on the helium to push it toward the outlet, if the outlet's uncovered, the helium's going to squirt right out. But they had an elaborate system of surface tension kind of baffles that kept and trapped fuel near the outlet of the tank, so that when the thrust came on and all the propellant went down where it should, it sort of recharged this chamber at the bottom of the tanks to keep it flowing smoothly and not lose all the pressurization. I remember the first, my impression of what reaction control jets would be like is based on science fiction movies where you see the spacecraft out there and there's little squirts of jets, you know, that nudge you around. And we went out to the ground test facility at White Sands on a field trip out there, where they actually had the forward RCS set up, and they were going to do real firings of the main jets out there. And we were probably a couple hundred feet away from the test setup, and we're out there waiting for the sequence of jet firings to start on a test. And the first firing of one of the main jets, which are right up around 900 pounds thrust, was just a short pulse. And everybody went about 3 feet off the ground. I mean, it was like you fired a howitzer. It was just stunning. Wham, wham, and it just blew you away. And the realization, we're going to be in the cockpit here, and these things are firing right outside the windshield. They did. In space, the ignition transient ricochets through the structure. You can hear this kind of booming effect. But once they're on, if it's a long-duration firing, it's silent. In the same way, visually, you can see a flash when the fuel is slid a little bit in front of the oxidizer to make sure you don't overheat something, and so there's incomplete combustion at the ignition. As you can see a flash go out there, but once on, during an ohms burn, for instance, when these ohms engines are firing and you're looking back at the aft, you see the flash and they're on and they're pushing and you can feel it, but otherwise invisible. That's the way you remember. Yeah. On the other hand, there are vernier jets, little guys. I don't know if they're shown here, but there's little 25-pound thrusters or something that's used 98% of the time on orbit. You really are doing the psst, psst kind of thing with the vernier jets, and you can't hear those or see anything when they're going off. In fact, we got everybody quiet and kind of held onto the walls, just trying to see if we could barely detect when a vernier jet fired physically in the cockpit. Interesting. The orbiter is one giant heat transfer machine. Lots of calories of heat energy pumped around from one end to the other, and so there's water loops within the cabin that transfer the heat to freon loops that are the fluid is pumped through the radiators to reject heat. There are, in spite of all these heat rejection systems, then there are heaters everywhere, whole banks of heaters to keep stuff from freezing. And then for the landing and takeoff phases, there are flash evaporators that flash water and or ammonia when you get down where water, when you're down in the atmosphere, you use ammonia to cool the loops. And of course, the payload bay doors are closed. So and it turns out STS-3 was a major test of it, was to test all these loops and how the structure responded to long durations in given attitudes with the sun shining on one side and cold space on the other side, and how the structure would distort, or hopefully not distort, and how all that system would work. As it turned out, you like lots of redundancy. This is probably the weak point, I thought, in the whole orbiter design. We got 3 engines. We proved that you can get there when only 2. But the Freon loops, there were 2 redundant through the radiators, and if one Freon loop pump quit, you're in a severe emergency. That means stop everything, power down severely, turn off all the computers except one, get in a proper attitude and be ready and go into a panic reconfiguration to come back and land. Originally, the design had 3 Freon loops. You could lose one and go on with no concern. But as it turned out, the heat loads were so high, and the weight criticality determined that all we had electrical power to run were 2 loops, and so we ended up with a single Freon loop, which fortunately, as far as I know, never failed. But if it had, it would have been a crash, deorbit, and landing under severely powered down conditions. So well, it's kind of mundane, and people don't think about it as a primary system. The thermal control really was critical. Payload bay doors. This is a busy chart, but it indicates these are really complicated. 60 feet long, and something like 120 little motor-driven latches to latch them closed. And you don't just go chunk close like the Bombay on a B-52 and it's closed. To close the payload bay doors, you get them close, and then the latches along the bulkhead, all in a zipper fashion, have to sequentially close, and then you go down the center section to latch the 2 left and right doors together, all software controlled and there was a lot of concern that we addressed on STS-3 particularly about whether this is all going to work. If you've been floating around with these pointed to dark space, would they distort to where the zipper scheme would work? We worried about it enough that part of our emergency training, contingency training, we spent a lot of time underwater in the neutral buoyancy tank looking at a system going out EVA with a series of come-alongs, you know, the kind of things you use to pull the motor out of a car, that kind of thing, that we could go down there and hook up and lash the doors shut, actually kind of manually get them shut and then latch them shut with these. Fortunately, that's never had to use, and this complex system has worked good. But it was scary the first time we flew it on STS-3. It was a big concern. Okay, what I got here, hydraulic system. Hydraulics are hydrazine-powered turbines that run at some ridiculous RPM, like 200,000 RPM to drive hydraulic pumps back here in the back end. And then they're crucial during launch because they got to hold the elevons in position, but they also got to provide the muscle to gimbal the main engines and keep you steering straight during launch. During entry, they're what you use to fly when you get back into a dynamic pressure situation, control the rudder speed brake, and the body flap. Body flap is a big surface that sticks out underneath the main engine bells and is a slow-moving trim device. The body flap is always moved. You go through this Mach 25 to Mach 0 envelope, and the trim conditions necessary with these big elevons varies a lot. So to desaturate the elevons and keep them in basically fared with the wing, the body flap's your trim device. And it's, you know, it's like this row of tables long and this wide. I remember asking to see the motor that it's driven a lot of mechanical advantage by a hydraulic motor. A guy took me around. I couldn't find the actuator, you know, for the body flap. He showed me the motor is this big around and this long, little hydraulic motor. So you can do anything with mechanical advantage, but didn't have to move very fast. Finally, on the system pictures here, the RMS, hopefully you've heard about this, is built by SPAR up in Canada. It's Canadians' main contribution to the orbiter program. Pretty magical device mounted along. It can go on either side, but for our flights, mounted on the left-hand side or the right if you're looking out the back windows at it, and had joints, logically called the shoulder joint, elbow, wrist joint, all electric motor driven. But the interesting thing was the control. You had hand controllers mounted in the aft part of on the right console in the back where you looked out, and you could work in a mode where you were actually driving the end, left, right, up, down, in, out, without regard to what every joint was done. That's all resolved by the software, and worked well. The end effector was a clever kind of a hollow cylindrical device that would rotate inside, and three cables that would be out curved around the periphery of the inside this cavity. When activated, you put this over a post on whatever you wanted to grab onto with a knob on the end. You go over the post and then rotate the inner barrel, and the cables would wrap up and grab onto the post, and then they would retract in to rigidize, and that was the grabber on the RMS. And we flew this on STS-3. I'll show you later. Okay, well, anyway, that's the subsystem review. Let me show you how things went during approach and landing tests. Now, let's see. I've got to get back to... I've never figured out how to embed video in PowerPoint, so I'm going to be doing it manually. Any questions while we're waiting on this? Come up. Well, this is the desert around where I live, and a Gila monster and a Joshua tree to set the scene. And here you have OV-101. The numbering system, as it turned out, is kind of interesting. They built OV-99 as the structural test article. Was strictly built to be in the lab and do all the structural testing on it. 101 then was the first orbiter built, the Enterprise, being hauled from Palmdale across the back roads and the desert roads to get over to Edwards in these scenes. And 101 was the ALT airplane. You can see kind of phony looking RCS. It had, as I mentioned, only the systems that you needed to fly atmospheric flight. So this was a big thing, getting it across country. It had a pitot boom on it. It had just simulated thermal protection, styrofoam painted to look kind of like they thought the space vehicles would look, but wasn't real. It was put in the mating and docking device, which is at NASA Dryden, where I work now, hoisted up, and then the 747-905, the first shuttle carrier aircraft, was pulled under, and they mated them up. I remember flying out to Edwards and seeing this unlikely combination, and I thought, the first time I saw the two together, I thought, they can't be serious, but then I realized I was going to be in it. So there were 13 total flights. This is a taxi test. When you got an aerodynamic test, you can sneak up, and so you do baby steps. This was just a high-speed run down the runway to see if it would rotate and anything would shake alarmingly, and that looked good. So preparations proceeded for the first of the captive inert flights. This is Fitz Fullerton and Tom McMurtry, both real good friends, and they were the crew on the 747 for this first milestone flight. A lot of people were out watching and wondering if it would fly, which it did very well, and off it went. You notice a longer front attach structure there, and the orbiter is purposely on there at an angle of attack to produce lift. I fly the 7-4 for ferry flights now to haul orbiters back to the Cape when they land at Edwards, as the last one did. And the nose, that front bipod is much shorter so that the orbiter's down for less drag for the combination. But this setup here was so that we could get the orbiter off the top and not hit the tail. There's a rumble. The crew noticed a shaking. It's still the case when you fly. These vertical fins were added onto the horizontal stabs to increase directional stability because the orbiter blanks a lot of flow over the normal vertical. And in fact, they overdid it a little bit. There's too much directional stability, which has resulted in the weird situation is your crosswind limit when you have an orbiter on board is greater than when it's not. Because you got so much directional stability in a crosswind, there's a strong weather veining, and you run out of normal rudder without an orbiter. But so you're good only to 15 knots crosswind with the orbiter on. The limit is 20 knots. And it's a good limit. I've flown them both ways in crosswinds, and indeed, at those numbers, you run out of rudder as you land and are rolling out. The strong weather veining tendency is leading you off the side of the runway. Anyway, that looked good. And so they came back, and we had a big post-flight party. ALT was great for parties. We had 13 post-flight parties. So after 5 flights, well, and at the same time we're doing the ALT flights, we're developing a shuttle training aircraft. This is a Gulfstream 2 with big side force generators on the belly, and it's an airborne simulator. The left seat is set up with the orbiter instruments, and the right seat was the standard Gulfstream cockpit. We've flown thousands of dives at the ground in the STA, preparing for the whole idea of first time for sure, unpowered landing that you have to do right the first time. And back in the simulator here for lots more runs it was a great time because everything was brand new, very interesting. This is a camera and an actual model. This is before the days of computer-generated video. So it flew the little camera down to landing. And we learned a lot about handling characteristics. One that we really wondered about when you made a lateral input to roll the orbiter in the simulator, it would bang you. There was this lateral lurch, we called it. It'd jolt you sideways. And we thought, this can't be real. It doesn't make any sense. No airplane we ever flew does that. We squawked it. They came back and said, well, equations all worked out, so we lived with it and thought it was just an artifact that was snuck in there and didn't worry about it. Now the captive active started, where we actually got in and cranked things up. On the second flight, I was chasing in the T-38, and Engel and Truly were in the cockpit, and I noticed shiny looking on the side. That big X on the CRT is what happens when the computer that's driving that CRT quits. That's sort of the panic symbol when the X shows up. Anyway, I noticed a leak, as it turned out to be. We had a severe hydrazine leak. Hydrazine is bad stuff to have leaking. And one of the APU supply tanks let go, plus they had an overtemp. So we found things that were wrong, and would have been, it made these captive flights worthwhile. If we'd just gone and launched off on the first one, it could have been more exciting than it needed to be. So we had 5 of those, and Fred Hayes and I got the odd-numbered flights, 1, 3, and 5. 5 more post-flight parties, and then we decided we're ready to go. So it was on, well, this is the last of the captive active flights. The scheme by which we planned to get off of here and not take off the tail of the 747 was that the 74 would go as high as it could go. It could get up to around 27,000 feet. With engines overboosted, Pratt & Whitney said you can go this long with extra power. And then nose over and speed up to 240 knots. It was climbing maybe 190, 200 knots. With a little downhill push, we got up to 240. At 240, the SEA pilots would go to idle power and air brakes up, put drag on the carrier. At that condition of 240 knots and at the angle of attack of the orbiter, it was actually lifting more than its own weight. So the result is we really dropped the carrier, as it turns out. There are 3/4 of a G difference between the two. And so when Fred, we get a lot of views for some reason of Fred's left shoulder. He's in the left seat, and he mashed the separation button after Fitz and the carrier aircraft hollered carrier ready. That is, they were back at idle with the speed brakes up, pushed the go button, and bang, off all 7 explosive bolts would blow. Control room was in Houston. Strange enough, we're talking to people back in the old JSC control room when we're out at Edwards flying these flights. But it was just like they were there. Okay, we're coming up on a condition, and this was in August of '77. All the ALT flights happened in 1977. You notice there's a tail cone on here. The tail cone was flown on the first 3 flights. It makes a big difference. It smooths the flow so that the buffet on the tail of the carrier aircraft was less, and it just about doubled the L over D of the orbiter. Okay, we're going to arm, and we'll get there. Get a go from the control, And we had two chases, one off to the right and one in trail separation. And just like the engineer said, and the load cells that we had on there testing exactly which way the thing was tugging before we did it, said we would do, straight up. This is slow motion. Nothing's leaking. This is vortexes off the wingtips causing condensation. And away we went. And the next, simultaneously, with this bang that shudders through the airplane when all these explosive bolts, a big X on the CRT in front of me. So we had cue cards, and I had, we'd practiced this, and my job while Fred flew, he actually got a vertical clear from this chase pilot, and then rolled into a bank and a lateral clear from the guy that was chasing from behind, and knew that it was okay to push over because we're only now at 200 knots, and we wanted to get to 300, and it took a considerable pushover to get up to speed. Meanwhile, I'm pulling circuit breakers on rate gyros and turning off accelerometers at our pre-planned procedure to accommodate flaws in the redundancy management. When you lose one computer, you also take out part of the sensors in the flight control system, and to be sure that a subsequent failure wouldn't put you in worse shape, it took about a minute's worth of manual reconfiguration on my part, and I kind of missed the whole first part of the flight. When I turned around, I realized, hey, this thing is flying good. It's smooth, and it's on speed, and Fred was flying. We flew a rectangular pattern out of a downwind leg here as we nosed over. And I got my chance to roll into a left 90-degree turn and fly base leg. And as I put the stick over to roll, we got this big lateral lurch, just like the simulator said. It just stunned me. Son of a gun, they were right after all. It's just the nature of something flying at high alpha and rotating about a stability axis, and the cockpit gets slid sideways. It's got big elevons, so it flies like a fighter, it really does, and you're doing it all with a little stick that doesn't move much. Anyway, we came down final at 290, I think it was, flared out. My job was to put the gear down, a critical function. And we're landing on Lake Bed 17 on the dry lake at Edwards, which is something like 10 miles long, so we're pretty good margins there. And Fred took the airplane back from me. I only got the fly base leg, but we touched down at about 185, I think it was. Nice and smooth. It was beautiful. The speed brakes come out to help cushion the derotation. Nose gear down. And we raised a little dust as we rolled to a stop. So it was a good day. And we had a really good post-flight party after this one. You can see the rudder speed brake flared there, and the elevons full up. And so now Joe Engel and Dick Truly did it again. A couple of weeks later, or thereabouts, they got their turn, and they did much the same flight, repeated it. And one thing, you see the pitot boom out there. A pitot boom is strictly on the Enterprise, put out there to get good air data out in front of this big blivet of an airplane, which is hard to get good measurements. There you can see, okay, let me get the next one going here. If I can figure out how to get out of this. Because the excitement came later. On STS-1, I looked out there when we were on final. I had time to look out and look at the pitot beam, and man, it's going through an arc of about 3 feet. it was built with the perfect resonance of everything else with the airplane, and it was just a blur out there going back and forth. And I really thought it was going to break off. But
was that your only pitot source, or did you have the normal ones in the?
Good question. Somehow we had at least inertially derived ones. Everything looked good, and actually it still put out good airspeed, even though it was a blur. And I think the beta averaged out, and so anyway, it wasn't a problem we noticed. Other than visually, it looked like it was going to break off. So they changed and stiffened it up, so it wasn't a problem on subsequent flights. Now you can see here we're at free flight 4 now, which was the other crew's turn, with the tail cones off. And our final approach glide slope with tail cone on was 11 degrees. With tail cone off, it was 23 degrees. Halves your L over D. So you're really in a steep dive. Normal ILS into Logan out here would be 2.5 degrees. So you're coming down gangbusters. And it's even worse in ALT than it was on the orbital missions, which were coming down with the same configuration, but much heavier. Heavier, you got more gravity working for you, and you can fly shallower. Doesn't seem to figure, but that's the way it is. So 19 degrees is a normal return from orbit, final approach glide slope. We were up in the 20s. Kind of catching up a little. One of our jobs with on the flight preceding this was to try the braking. We just let her roll out on the first couple flights. They wanted to do brake tests, and Fred jumped on the brakes after we touched down, and another resonance problem. Interaction between the structure and the anti-skid, which is, and I thought it was going to break the airplane. It was just violent, shuddering, shaking, everything rattling in the cockpit, and I hollered at Fred, "Get off the brakes, we're going to break something." And he said, "Nope, the card says we got to do max braking." I was pleading with him to get off the brakes, which he did. Easy fix. When they flew the next flight here, they did hard braking, and it was smooth. They went into the change the resistor and the feedback electronics, and that did it. I mean, it was instant fix. So it says there still is reason to do flight tests because surprises happen. Okay, so now free flight 5. It turns out that there was a little break here. We're back at Houston, and Prince Charles, he wasn't married yet at that time, but he came by on a visit, and we gave him a ride in the simulator. He'd had some flying time, and he got into horrendous PIO. I mean, he was out of control and crashed in the simulator and felt bad. And we said, "Nah, it's because you're not used to the stick and everything." And that was his tour. So now for this flight, he was actually out along the runway. They had him out there so he could watch. And the objective here was to land on the concrete runway, put it right on the line. There's a white line 5,000 feet down. And Fred was really working at it, putting in a lot of inputs. Look at the elevons going there. You see them? And he's making roll commands, skip. And so we logged a couple landings. And down and rolled to a stop. And when afterwards we called out, and he came up to say hello and said, "Oh, you made me feel good. You guys did as bad as I did." There he is right there with his binoculars. Well, it scared everybody to death. It looked worse from outside than it did in the cockpit, and the flight control flaw that we found, though, was serious. You got elevons that do both pitch and roll, So in the software, when you're asking for both pitch and roll at the same time, it's got to decide which one do I move. I'll stop this. It's just all supposition of what would come. The software has to give priority, and they decided to give priority to pitch. And roll was sort of taken second priority when you had to limit the commands to the elevons to within the capability of the hydraulic system. So the result was a lag in roll response when you're working pitch hard. And the lag was up around 0.2 to 0.3 of a second. You may be aware, if you've studied flight control system. Any kind of system that has 3/4 second delay between input and response is asking for a PIO, pilot-induced oscillation. And we had a big time in roll. Fred was clanking back and forth, stop to stop and roll, trying to level the wings after that first skip. I heard the controller banging over there, and I suggested if you get off, maybe it'll damp, because we're doing this. And sure enough, that's what he did. He stopped the inputs. The airplane damped right away, and then it went okay. But there's something that we had to fix, obviously. Here's a picture just microsecond after liftoff on one of the last two. Well, the decision, there was a lot of debate about do we go back and fix the flight control and fly some more ALT. But this is a huge production. It was costing time, and we weren't getting into orbit. A decision was made, now we'll do it in simulators and in-flight simulators and fix the problem, but press on. So that was the end of ALT, at the end of which, when you do flight tests, you talk about opening the envelope of an airplane. Well, the envelope of the space shuttle is 400 nautical miles altitude and Mach 25, and in ALT we got to 4 miles and 0.3 Mach. So it's really down in the lower left corner, but worth doing. Test results, I've mentioned as we went, we had that APU fuel leak, fixed it, didn't come back. The Buffett lift to drag was right on what we expected, no surprises there. Handling qualities were good, even with the lurch. It was not a problem. Mentioned the pitot boom, the anti-skid, the SCA did the job, although it struggled to get us up to, with the tail cone off, it could only get to about 18,000 feet. So this was not a good program to build up your flying time. I got it was about a total of, in 3 flights, about 12 minutes of flying time. And the biggie I mentioned, the handling qualities, the PIO tendency that we fixed with lots of studies later and changes in the way the control equations were written. And as a final thing, they did some more flights with the nose lowered down and determined what the ferry flight performance of the combination is. I have later, after flying in space, checked out in the 747 and still fly it on the ferry flights. And it does the job. It burns lots of gas. I figured out that the combination cross country, the mileage is about 300 feet per gallon. So football field per gallon of fuel, 40,000 pounds an hour, so there's a fuel flow. It goes about 1.5 times its own length on a gallon of gas, but gets there. I don't have to buy the fuel. A lot of people said, wasn't this scary, ALT? Actually, from a risk standpoint, we had ejection seats. So if anything had gone wrong anywhere along the line, we could have pulled the handle and jumped out. The scariest part of it was when we got in, and during the captive flights, we just walk up the stairway and crawl through the hatch, and the same way getting out. But after the captive active flights, we'd land still on the orbiter. And they had this cherry picker to get us out. Now, the situation here, it's a round hatch hinged at the bottom. They only wanted one person at a time on the end of this thing. So you open the round hatch, and then they bring this up, the guy on the ground, and he doesn't want to get too close and ding. So he leaves about this much of a gap from this round hatch, which is 60 feet above the ground, that you got to crawl out on your knees and then stand up and then make the leap across the thing onto this wobbly cage up there. But that's how our captive actives went.
Were you wearing flight suits for all these tests? I mean, you had ejection suits.
Yeah, but we're wearing regular flight suit, helmet, like you would in a F-18 or any fighter. Yeah. Not pressure suits. We didn't have a severe cabin pressure risk at 25,000 feet. I put here let me get into the full screen mode here. Some thoughts about what's different when you test an aircraft versus a spacecraft. Well, airplane, you can do little baby steps, incremental tests. You can do static runs of the propulsion up to the full power in the airplane itself. Then you taxi it slow and then faster and faster down the runway. You can rotate the nose a little bit. The first flight you'll fly slow and leave the gear down and then land soon and check everything, and you can hold off till perfect day to do it. And then you go faster and faster to expand the envelope. If anything goes wrong, you can peel off and get back on the ground quick. And as I mentioned, you can always pull the handle and bail out if things go really bad. You got a spacecraft, it's all or nothing. You got to use the propulsion at its full power. All the critical subsystems have got to work. You can't make a quick abort. Long delays, like days, are sometimes required to get back to the conditions where you can make an appropriate landing, and the weather can turn sour at the time. So when you're going to flight test a spacecraft, you've got to have a lot of redundancy in the design to allow for the bad day that has to carry you through a considerable amount of time. You necessarily got to test everything to the limit. Wind tunnel, CFD, thermal vacuum, because the environment is lots more stressful. You got to have a lot of instrumentation so that you can tell what did go wrong or be sure that everything went right. You're talking about an army of controllers in a control room to pull it off with a complex system like the shuttle. And lots of simulation to get everybody trained. A biggie is to verify the software. I mentioned the software is guaranteed to be wrong on the first release and several subsequent. It's just the nature of building software. And so getting that checked out is a major one. And procedures. When we flew the orbital flight, the checklist, the stack of checklists just laid on top of each other was about this high for a 51.5 and it weighed 210 pounds just to call the flight data file. And then lots of time and expense getting everybody really ready to go and being sure that when you're going into an unknown part of the envelope, that the margins on the flight control are adequate, so the surprises and the aeroderivatives that hit you can be accommodated. I've rambled on a long time here. We could take the 5-minute break. I can answer questions, however you want to do it. Maybe it's time for a stretch.
Questions? 2-minute break.
2-minute break.
These people are tough.
All right, break's over. Okay, the next assignment for me was being put on a orbital flight test, and specifically STS-3. Two-man crew, Jack Lausma, a Marine, and myself from the Air Force. We were in pressure suits, you noticed, there, and on ejection seats in the Columbia. This is OV 102. 101 was the Enterprise, 102 the Columbia. And our countdown went smoothly. This was in March of '82, and this is a signature moment in your life when the SRB's light. There's no doubt. I mean, it looks smooth and nice as we're flying through a cloud here on launch. Logging weather time, I might add. But it is rough and noisy and rattly, and the acceleration is right away, and it builds up to 3 Gs when the main engines are throttled back to hold 3 Gs, and so it's no doubt you're on your way somewhere really fast, wherever the solids want to go. Everything worked good right up to MECO, and the external tank, as you saw, drifted away, and then here come the first order of business, opening the payload bay doors so we can start rejecting heat with the radiators that are mounted on the inside. We're tailed down, and as you watch here, we're going right over Los Angeles at the time. This is just north of LA. You can see the right. This is LA, and this is Santa Monica and LAX and Palos Verdes right there. Anyway, the first thing we had to do is get out a theodolite, that is a sighting device that surveyors use, and take a daunting number of readings on little targets that were pasted around inside the payload bay and on the doors as to measure where they were, and we did that through the flight all the way along. Wasn't fast enough. Out in front of the nose there were some dark patches. That's where tile were, white tile, and fell off during launch. They actually found some washed up on the beach. Fortunately, none of the black tile on the bottom fell off, but we did lose some on the top. Zero G is really one of the delights. There's two really good things about flying in orbit: weightlessness and the view out the window. And it's like nothing that you experience even flying high-performance airplanes. We had the RMS cranked up. That was my job as the RMS operator, and we had a package in the back, the plasma diagnostic package, to grab and move out there. Here's some scenes that show you the housekeeping area. In the corner there is the John. And long-duration space flight exercise is important. It's really not a big deal on a 7-day flight. Jack's a Marine, as I mentioned. He's got to have his daily ration of push-ups. So here he goes. How about a one-handed push-up, Jack? How about a no-handed push-up? This is a quick summary. We went our 7 days, and the lake bed at Edwards had a really wet spring. It was unusable. So we went to White Sands, New Mexico. First day, right as we're about to light the OMS engines to start deorbit, they said, hold off, because this terrible dust storm was going on. And we waited a day, a delightful day, with nothing in the flight plan much to enjoy ourselves, and then came down the next day. Now we found another gotcha in handling qualities here. Right here, Jack thought the nose might be coming down too fast and tried to stop it and ended up doing a little wheelie. And subsequent analysis showed that the whole response of the vehicle changes when you're down on the main gear only. And nobody thought of that. You know, it would seem like, they're worried about pitch in the air, but not while you're rolling on the main gear trying to derotate. So it resulted in more software changes. Another thing we learned, they were pushing for auto land, and so we flew the whole turn onto final and down final hands off in auto land. The program wanted to take this out of the hands of the crew. So here on the third flight, they had us sitting there watching the airplane fly down to pre-flare, and then the first chance Jack got to grab the stick was at the last minute to do the flare and landing. That was dumb. When you look back at really dumb. And so now all flights, commander, if it's been auto down to 40,000 feet where you go subsonic, will fly manually all the way down to get a feel for the airplane. Makes a lot more sense. So that's the way flights are done now. Here's where we started. From orbit, this is how Cape Canaveral looks. Right here is the shuttle landing strip that's down there. You can see it, and the launch pads are these two dots. And so that's where usually a shuttle flight starts and ends. Here's a picture of our payload bay on STS-3, and we did have a payload. Previous crews had pretty much empty payload bay, but we had an environmental measurement thing, a lot of instrumentation, and this PDP, that plasma diagnostic package, that we actually had something to grab with the manipulator arm, as you see here. I looked around, I found, I don't know if you can recognize this, but that's Cape Cod right there. Picture of MIT. Not a good picture, but there's got to be lots better ones. And here's where we ended up, the White Sands area near Alamogordo, New Mexico. Okay, what did we learn? This is a pretty cryptic summary. Training was a real problem. The first two crews that flew STS-1 and 2 had all the attention of the training people and the simulators. They had priority, properly so. We were, on the third flight, had low priority and really struggled, and we found when we got in the simulators that when they didn't work right, nobody could explain why, many times we try an ascent and crash and burn, and you always were scratching your head. Is this real? Is this the way the orbiter flies, or is it some flaw in the simulator? So early on, you're developing not only the orbiter, but the training facilities. And the people didn't understand the system. We had more exposure from ALT to subsystems than the people that were supposed to be the experts. So it was a group learning process, and a long way from what happens now when crews go in and they get the straight word right from the beginning on how things are. The tiles fell off. Not good. They changed the bonding scheme, improved the quality control, and fortunately for the program, no critical tiles fell off. But that was alarming. We looked out there, we reported it, took pictures of it, looking at these gaps in the system right out in front of the windshield. But the ground said, oh, don't worry, that's a cool area during entry. Entry's at 40 degrees angle of attack, so it is cool on top. They were right. Everything was fine. But another tile thing was after the flight. Well, actually, delay that. It was really more after the next flight. I mentioned how the ride is. First 2 minutes are rough and exciting. The next 6 or 7 are smooth, unbelievably smooth when you get on the main engines. any more vibration than you're getting sitting in the chairs now, and just a steady, relentless push. It's a spectacular ride, but you're back in the seat. Had a APU oil overheat during that 3G part. Actually, about 2 minutes before MECO, the ground called and said we need to shut down one APU. We're up past the point where we could live without all 3 APUs running. So I had a chance to test what I worked on years previously. When the cockpit design, you're concerned about visibility when you're squashed in the seat at 3Gs, and access. And the APU switches, we had to put them down here, and I worried, I remember worrying specifically, if we got to get to the APU switches, the guy in the right seat under 3Gs, can he lift the helmet and look over there and find the correct switch, and you do not want to shut down the wrong one of the good ones. And it turned out, I guess with the adrenaline, lifting this heavy helmet at 3Gs, I did it without even thinking about it and went right to the switch. So it worked. General habitability was good in the orbiter. First time anybody lived there for 8 days. A good way to think about living in the orbiter, think of it as a camping trip. You know, you go on a camping trip, you don't worry about hot water and showers and all the niceties of home. You get in that frame of mind and it's fine. The food's adequate, the facilities are okay, although in our case the toilet ground to a halt. It's a drum that rotates to centrifugally sling all fecal material out and contain it, and it ground to a halt. So we were into a real camping trip for a while on that. Although it worked out. The ARM worked great, RMS. The main jets I mentioned earlier fortunately don't use the main jets much. It'd be hard to sleep with them booming away, but you use the verniers most of the time. Verniers are critical to smooth operation over long periods of time. We spent a lot of time, for instance, tail sun. For like 3 days, we put the tail right at the sun and stayed in that inertial attitude, and so it cooked the back end while the front end of the orbiter is cold, and we took all the theodolite measurements, opened and closed the doors. All of that worked fine. The systems handled it. A lot of it was ground analysis, and how the temperatures were extensively instrumented. And we did notice a strange thing. It's not strange, but it became apparent when you're in orbit. When you're on the sunny side of the Earth, I mean, it's as soon as the sun comes up, it is high noon bright. But there's no atmosphere around to diffuse the light. So when we're tail sun, it's hidden behind, perfectly eclipsed by the aft structure. And so there's no small sunball to be seen anywhere, even though it's bright sunny from just the reflections of the structure you can see out the window. I noticed looking at the radiators, which are very, very smooth, concave surfaces out there and shiny silver colored, and it looked like there were bright diamonds all along the surface when we were tail sun, and finally figured out what it was just little specks of dust on the radiator, which you wouldn't even notice normally. But tail sun, with exactly tail sun, the sun's rays are coming right down exactly tangent to that surface, and the least little thing on it would flare. And interesting effect, which took me a while to figure out what all these bright spots on the radiators are. Entry on STS-3 was done to about 9 o'clock in the morning landing at White Sands, New Mexico. So we started the entry halfway around the world. It's dark, and most of the entry was in the dark. And the plasma light show that happens as you get down in the atmosphere and the ionization that happens produces spectacular scene out the windshield. I mean, it also had us thinking about the missing tile that are going. But a night entry is really a show. My next flight was a day entry. It's not nearly as spectacular. Mentioned about grabbing the stick too late, unfair to Jack, and then the derotation. Okay, now on to part 3. How am I doing? We might make it yet. STS-51F was a whole different situation than the earlier test flights. One big difference, there were 7 people instead of 2. With 7, we had to add a little bit on the patch to put the extra 2 names. This is the 19th flight. There's 19 stars. It's primary experiments. This was a science flight. It was a space lab, but without the laboratory. All equipment in the payload bay full, stem to stern, with telescopes mostly. And all the telescopes mounted on the pointing system we had were solar telescopes, so we had the sun in the accurate part of the sky. Here's Orion and what is it? Leo, the backwards question mark, yeah. And 19 stars, the 19. A lot of symbology here. Okay. Let me, a short, entertaining video. Do the short one here. Now we had 7 people, included 3 mission specialists, which Dr. Hoffman was when he was down in Houston. And we had 2 payload specialists, guys who were not full-time astronauts. They were solar physicists, and they were the experts on the solar telescopes that we had and went along to fly. Our first try here at main engine ignition ended 3 seconds after ignition. We felt the spacecraft rock around, the noise, and then nothing. And we had a pad shutdown because the left engine, the automatic system detected a failure, a slow-acting valve, and it shut us off. So we're there wondering if we're on fire and whether we ought to race out and so forth. So it was tense for a while, but there wasn't any fire, just this automatic shutdown. So we crawled out. We're told there'd be a 2-week delay. So I went down and we took the kids to Disneyland and had a good time, went back home and started the whole training cycle again, and came back 2 weeks later and got a good start this time. But not after lying on our back on the pad strapped in for 5 hours because of some software glitches that had to be fixed, and computers reloaded and tested, and one of our reports was that 5 hours is the limit. I mean, you're lying on your back with your feet up in a pressure suit strapped in. That's more than is reasonable to ask prior to launch. On the way up, well, I'll mention it later. Here's the instrument pointing system. This baby was built in Germany. It's this device, this gimbal device, that held these 4 solar telescopes and the star trackers. Here's a physics experiment. The OMS engines are lit. It produces 1/16 of a G, the thrust of the orbital maneuvering engines. If you're trying to sleep, that's what happens when the OMS engines come on. And you saw the water going across. it's deja vu. We had the same old PDP package on this, but with a difference this time. We took it out of the payload bay, brought it up here. That's my right ear you're looking at in profile, out the window. It's crowded up there. It's 7 people up on the flight deck, all trying to get a view here, but we let go of it. And then it had a momentum wheel in there to cause it to spin up slowly, and we backed away from it, and we flew a couple of very challenging loops around it. Here's a sequel to the hairbrush. This is not me, it's Story Musgrave, who has the same hairdo as I do. And he's getting spiffied up for the TV show. That's how we did, is horse around for 7 days. Got extended a day to 8 days again. And this landing was back at Edwards, runway 23 in August 6th, when it was 105 degrees, lots of heat waves. This landing was by far the most forward CG, because we still had all that equipment in the payload bay. And we were almost the heaviest orbiter landing. So getting the nose down before it fell down and crashed and broke the nose gear was one of my primary concerns on this one. Okay. Back to PowerPoint here. More about the actual launch itself. There's the customary view. They put a camera right in close and got this really close-up view. But it was about 5.5 minutes after this picture. We had delayed 5 hours. It's late afternoon, so very quickly, heading out over the Atlantic, we were in darkness. And then, bango, remember it had been the left engine that got us on the pad abort. Well, the center engine shut down. We were at 3 Gs, all of a sudden we're at 2 Gs or something like that. Instant square wave cutoff in acceleration. And looking there and confirming, and the center engine shut down. What had happened was that there are a number of sensors on the main engines. The particular one that got us was the fuel high-pressure turbo pump, a piece of machinery running at 75,000 RPM, high pressures, the high-tech gear that makes the main engine so efficient, high ISP, but really run at the limits of metallurgy and technology. And the sensor that senses the output temperature was a series of 4 platinum wires in a cavity in the output of that turbo pump. And they had some tendency for the wires to burn through. When they burned through, they showed overtemp was the electrical result of a burn through of one of these sensors. Well, we had 2 burn through, and the software said that must mean there's 2 sensors say you're too hot. I'll shut the motor off, and it did. There was no reaction. We just kept going straight and smooth. But it was now put us into what's called an abort. Well, here's the crew. I got 7 of us. Need to practice this more, but anyway, it was a 2-shift operation. We were going to work around the clock. So we had a red team and a blue team. And I was a commander, so I had a striped shirt. abort to orbit. We had to call from the ground, confirm what we knew already. It means turning that rotary knob to ATO, abort to orbit, kind of an oxymoron in a way. It's not really an abort. It's pressing on and pushing the button behind it. It modes the software in to do a couple things. Lower the insertion target. We had tried to get as high as orbit as performance would permit, but now we're going lower. Engine down cost you total performance. And we also started dumping OHMS fuel. We had to turn on the OHMS engines, and we ended up dumping 4,500 pounds of OHMS fuel, a little bit of extra thrust, but a significant loss of weight to allow the remaining performance to get us to an acceptable orbit. And interestingly, the last sim we did on training in Houston before we went to the Cape to fly, about 2 days before, was an integrated sim where we're tied into all the controllers and everybody's working at a team. And the very last run we had was an ATO, an abort to orbit. And son of a gun, that's what we did. We'd always had trouble starting a watch, and you try to do everything internally on the crew so that if you lose comm with the ground, you can complete the emergency properly on your own. On ATOs before, we had to start a stopwatch. At the time we started the OHMS dump, and we had a chart to go in to find out how many minutes of OHMS dump we needed to do given at what velocity we lost the engine. And Story's job was to do the watch, and in the excitement of all the other stuff we had to do to get the OHMS on, we'd always forget the watch. But this time he got the watch going, so we actually did it right. And we knew that when we got to where we burned out all the available fuel, which we did, we went to a fuel depletion cutoff, that we'd be really close to having to do right away another OHMS burn to get an acceptable orbit. We're right on the boundary. As it turned out, we dumped the right amount of OHMS. It put us, with every last drop of main propellant gone, we were just on the boundary of not having to do the first OHMS burn, and we could relax for 45 minutes later, halfway around the world, to do the final circularization. So it worked out good, except we were in a lot lower orbit than we had planned. And everything about this Space Lab flight depended on the orbit, so we were into a giant replan. Here's a nice picture of the IPS.
I also explained the situation of the inhibit switch on and off, and I don't know how much you were aware of what was going on there in the cockpit, but it was.
There's a switch in the cockpit that you have a lot of parameters that are monitored in the software on the main engines, which if they go out of tolerance, will shut the engine off. In fact, that's exactly why we lost the center engine. But right after that engine shutdown, we're in a state where we really don't want to lose another engine, because if we had, with only one left, we did not have the performance to get to orbit. We would have had to have gone to Zaragoza, Spain, and land in the middle of the night where it was 10,000 foot overcast and raining. And I mean, if we'd pulled that off, we would have deserved some kind of medal. So, as a pre-planned procedure, when you lose one engine before the point where you can stagger into orbit on one remaining engine, you inhibit the limits. You throw a switch that says, okay, now you're telling the engines to keep running regardless of overtemps or anything, because you take the chance, which is a big one if something let go, to not be susceptible to the same thing that got us for the first engine, that is a sensor failure. And so we did that. We inhibited the limits until we got to a point in the energy profile where we were pressed to MECO. That's the call, pressed to MECO, which means that you're now at a velocity where you can make it into acceptable low orbit on one engine if you should lose another one. At Prestamico, then, the plan was we'll re-enable the limits so we're not hanging it out on a possible second engine failure, and we'd accept a second engine failure because we know we could make it on one engine. So we did that. The call came up, we went to enable, and then before we got there, we got another call from the ground that said, go back to inhibit. Well, it wasn't time to get a full explanation. We dutifully did it. What they saw on the ground is more failures on the right engine. Remember, the left got us on the pad abort. The center engine shut down on the way up. And to make everything equal, the right engine, the same sensors they could see on the ground, it's not visible in the cockpit, each of those 4 platinum wires, and they saw those starting to go. Clearly a design problem here. And because they could tell those are going to go and get us that second engine, so that's why we went back to inhibit for the rest of the way. So it was made a good war story, but we got there. And we started operating the IPS. The platform built in Germany with all the telescopes. These are star trackers to align where it is, and this baby could point. The spec was 1 arc second of accuracy. An arc second is the size of a dime if you're standing at the Capitol and looking at a dime at the Lincoln Memorial. That's how much it's tens. But when we cranked it up, it didn't work worth a hoot. They just couldn't get it to stabilize or point where it was supposed to. And for 3 days, the payload specialists and the MSs were in constant communication with the ground, and they patched the software in a major way and kept sending up new software loads to get this thing to work. And voila, on the 3rd day, they finally got it right, and then it worked well and got a lot of good solar science. Just an aside, when you're looking at pictures from space, you tend to think, you walk around out here, the atmosphere is this big ocean of air above you, right? Lots of air way up there. This little bitty blue line right there, barely perceptible, that always appears on any sunlit picture showing the limb of the Earth, that's the same blue as the sky, the scattering that causes the sky to be blue. And that's all the thicker it is. It is just this little thin shell of atmosphere around, at 18,000 feet, 3 miles up, you've lost half the atmospheric pressure, and that's laying on a 8,000 mile diameter globe. And so and that's where all of human history has happened, in that little shell of air laying around the globe. Philosophical point for you engineers. What's flying on orbit like? Well, it's one of the 215 pounds of checklists. Here I'm checking propellant usage against what we got and where we are, because we dumped 4,500 pounds of crucial fuel that we needed to make the plan most maneuvers had ever been done in the orbiter on our mission. And we really worked we didn't want an extra blip out of an RCS thruster, and it worked very well. We got through 7 days and even had enough to have another day of science on the 8th day. But flying is mostly watching the clock. Everything happens according to time, and since you got 16 sunrises and sunsets every 24 hours, you never know what time it is without looking at a watch. And you're looking at a crew activity plan with everything laid out, and so we even had an alarm system you could set in the CRT to make a tone to wake you up. So a lot of clock watching to pull off a complex mission like this. It's just the way life is on orbit. Now here's one of our really serious high-level scientific objectives. This was the official name, the carbonated beverage test. Some, I don't know if it was an MIT guy or not, he's a real serious academic type, an Indian, I think. Anyway, he built a Coke can that had a lot of pressure regulators in there and laminar flow annular things. So many so that this Coke can only held 4 ounces of Coke. But he talked the White House. Reagan was president. Somebody on the staff approved, going to fly these Coke cans and see if they had a system to provide pop in orbit, you know, with the regular kind of carbonation and dispense okay. So we got the briefing and we had the 4 stowed in a locker, and I got them out at the start of the test. But 30 days before launch, all of a sudden this big thing came down. Pepsi got wind of this experiment and went to the White House staff, and they got Pepsi put on. Pepsi went into a crash program to fly 4 cans of Pepsi. So here's Carl Henneis trying the Pepsi. You notice that looks a lot like a shaving cream can? Well, that's how the Pepsi came out, just like shaving cream, this frothy ball of stuff. And I mean, theirs was a last-minute deal. It didn't have any pressure regulators in it. It just blew out there. And now we worried about having to make a judgment which tasted better. Well, the problem was we didn't have any kind of refrigerator, so they're both warm. So warm pop is not my favorite, and so they were not anything that anybody fought over either kind. But this was okay. If you let the Pepsi float around, it would coalesce a little CO2 in random fashion, but the physics of it, Carl found by blowing very carefully on the edge, you could get it spinning up. And spinning Pepsi would have the froth at the poles and the liquid around the equator. And we always had a towel guy standing by in case it drifted into something. It was getting pretty close. And this is the end of the experiment here. And how he got it in his mouth without touching any of it. We had that same PDP, but as I mentioned and you saw in the movie, we let go of it. We actually maneuvered all around the orbiter and looked at the wake through the plasma, let go of it. The proximity ops were very extensive and challenging in many, many maneuvers. That's in the Caribbean, the tongue of the ocean, a spectacular coral reef around very deep water. Here's Gibraltar. The rock, I believe, is right out here on the point. Mediterranean there and the Atlantic here. You've heard you can't see borders from space. Not true. This is Israel this way and Egypt this way. And the Gaza Strip along here, which has been in the news as of late. And in the same area, the Dead Sea, the Sea of Galilee. Here's most of Israel in one picture. A little closer to home, this is most of New Jersey. Long Island, there's Manhattan. Hudson River and East River. There have been about 10,000 copies of this picture. This is Southern California. This is San Diego right here. Los Angeles. And in a high-res print, you can see water here, which is San Francisco Bay. And the center of it all is the Antelope Valley right here, where I live and where Edwards is right here. This is the San Andreas Fault right through here. Closer up of LA, which at the end of 51F, we came right by Catalina Island, right up the Harbor Freeway and into Edwards. We went by Harbor Freeway at about Mach 3. And closer up of the dry lake at Edwards, and the landing, flight test results, which most of which I've mentioned already. And to finish up, I've got reports on a memory stick here. The pilot reports we wrote as crews, which you can take at your leisure if you're interested. Copy it off, and they're available. Not great works of art, but the specific things that we learned on doing the flight test. And these are just thoughts of transitioning into operation from test mode, which I got to see the whole gamut from beginning to full operational. So I apologize for running over, but
I don't think anybody minded. As you see, everybody's listening very rapidly.
Still here, yeah.
Thank you very much for taking the time.